So this is our last 40. This is our last 40 minutes. So this is where we left off. The value of our doing regression is that we can look at what would be the value of the dependent variable if our independent variable is zero or our constant, which is basically what the intercept, or what we call the constant, is when the independent variable is zero. In our demonstration, our independent variable is the IQ. And so if the IQ is zero, our expected NCE will be 14. And because we have a statistically significant regression coefficient with a standardized beta coefficient of 0.221 with a p-value of 0.039, we could predict that for an increase of 0.15 in our IQ score, we could expect a 1-point increase in our NCEE score as well. So that's what regression modeling is all about. We fit a line, and it has a very specific mathematics, and that it shows you what could you expect for every increment of the independent variable. What would be the increment also of your dependent variable? So that's what regression, that's the beauty of regression analysis, of simple linear regression, because you cannot get this value with simple correlation. When you do simple correlations such as Pearson R's, it just tells you that there was a relationship, and that the relationship was weak because it's 0.221 was the value of your Pearson's R, and that it only accounts because the R squared is 0.049, which only accounts 4.9%. So those are what you can get in correlations, but regressions can add more predictive value. And this is the most important output, is the standardized coefficient beta and the standardized coefficient beta, because it tells you where the model is when the constant is zero, when the independent variable is zero. So in our case, the independent variable here is IQ. So when the IQ is zero, you know that the NCEE score is set at 14. And in a model where the mean score of the NCEE was 30.27, and again, that's the model summary here. Okay, so that's very important to really look. And then we look at also the different residual, because it needs to meet the assumption of regression. Similarly, just like ANOVA, regression have assumption that must be met: homoscedasticity, heteroscedasticity, and heteroscedasticity is illustrated by this graph, scatter plot. My apologies. This regression standardized predicted value. And then you also have in your y-axis the regression standardized residual. Residual is for your y, or dependent variable, and regression standardized predicted value is for your predictor variable, which is your independent variable, which is, in this case, is your IQ. And it should look like a bird's nest. It should be scattered. And if I put a line on this one, right here, okay, right here. So using the equation of, using the linear equation, if I put a line and using linear regression, see this? This is where you know that both y-axis and the x-axis is that all the data are nicely scattered, because this is not your scatter plot of the IQ and the this is not the scattered plot of the IQ and NCEE. These are standardized residual. This is standardized predicted value. These are all regression, standardized residual, regression, standardized predictive value. And so when you look at this line, you can see that all of your observations are nicely scattered. Very different than what I have done here. When you have a scatter plot of your NCEE score and your IQ score, you get this. This is the intercept, which is the constant. And it is roughly, this is where the y-axis and the x-axis meet, and it's not very steep. It's not very deep. So that tells you then that when you look at this value of the studentized IQ score, you can see it's not very steep. The change, it's like for every 0.15 change in IQ score, you will get a 1 point increase in the NCEE score. That's basically a reflection of this intercept, that it's not very steep. It's very small amount of changes will create a small 1 point increase in the NCEE score. If this intercept would have been so steep, if this intercept is somewhere here, right here, if I draw a line right here, if the data would have been around right here, so it's a very steep intercept, very deep intercept. What that tells you then is that for every, this value in the this value in the unstandardized coefficient of the independent variable would have been very high, because it has more predictive power. But again, the predictive power here is also very weak. Just like the correlation was weak in Pearson's R, it's only 0.221, and that is a weak positive correlation, because a strong correlation should start around 0.6 and higher. That is a strong correlation between two variables. All right, so now let's move on to another type of regression. What happens if we do logistic regression? So this is when the maximum likelihood estimation will kick in. Because in simple regression, that was just ordinary least square. That was the mathematics. Now let's go to maximum likelihood estimation, and then let's go to logistic regression. So logistic regression is a regression that is used to obtain adjusted odds ratio. It allows us to build a model that examines the effect of several independent variables when our dependent variable is binary, which means two outcomes, yes, no, yes, no. Very appealing in epidemiology because our dependent variable only have two outcomes, and it's binary. It's not continuous. Unlike in our first example, our NCEE is continuous. This one, it's binary. It's nominal. It's yes, no, yes, no. And then, but our independent variable could be continuous, could be nominal, and then it's just really amazing how this mathematics will kick in, the maximum likelihood where it creates different iterations. Logistic regression allows us to obtain adjusted odds ratios. So this is an important concept, that it uses the odds ratio and it assesses the unique effect of the independent variable. It allows us to identify the best fit and the most parsimonious model. Parsimony means least. You know, the most the least eloquent model, which means it's not complicated, parsimonious, to describe the relationship between the dependent variable and the set of independent, or what we call predictor variables. It gives you a rough estimate of the amount of the variance of the dependent variable as explained by the model. So model building is the key, and remember that simple linear regression, logistic regressions, and later on we will move on to multiple regressions, are all under the umbrella of generalized linear modeling, which utilizes the OLS or the MLE mathematics. So an odds ratio, I'm not going to belabor you with this one because we already covered this in statistic 1. So that's why it's so important that when we go to logistic regression, that we understand odds ratio and risk ratios, because this is what the fundamental values that are being used in the logistic regression algorithm. I'm not going to go through all the math here, because these are just an illustration on what odds ratio is all about. And then this is the research question that will be answered by logistic regression, is that we have a binary dependent variable. For example, if our binary dependent variable is that, you know, whether going out more than 5 times a week or not going out more than 5 times a week will be a predictor. It comes to the different independent variable, such as trying to lose weight and such as gender. So right here, when we use the following question in a logistic regression, what is the effect of going out frequently on trying to lose weight once gender is controlled for? So the dependent variable is how frequent of going out to eat, such as you have two only, it becomes you need to make it binary, whether you go out more than 5 times a week, or less than 5 times a week, or more times per week. So it only goes 2 directions. It's 2 categorical binary variable is the dependent variable, because it uses odds ratio as the fundamental mathematics. And then our independent variable will be gender, male or female. Another independent variable is trying to lose weight in the past year, yes or no, yes or no. And that is a dichotomous variable. These are the different assumptions. The dependent variable has to be dichotomous, only 2 categories. The independent variable can be of any measurement scale. It could, but however, the results are most interpretable when the independent variables are also dichotomous. But we can do polytomous independent variable. But once it becomes a polytomous independent variable, we have to create a dummy variable in order to have a reference value. And I'll explain that in a little bit. So using a dummy variable is a way to express that a nominal variable with multiple categories by a series of dichotomous variables can be compared to one category, such as your reference category. So the number of dummy variables created will be one less than the number of the categories of the variable. For example, if you have a total of 4, then you have to minus 1, and then you create a three total variables. So for example, here we have a race or ethnicity, non-Hispanic, non-Hispanic white, non-Hispanic black, non-Hispanic Asian, and Hispanic. So you have, if you want to use a logistic regression, we would need to create 3 variables to represent the 4 categories. So it's 4 minus 1 will be 3 categories in logistic regression. And we need to put these variables into a logistic equation. Instead of the 4 category, we use 3 because we need to have a reference so that we can interpret it. If we don't have a reference, and if we don't create a dummy variable when we have a polytomous independent variable, then we cannot interpret what is the value of our independent variable in our regression model. So for example, here, if we have 4 total variables, we have to minus it with 1, and then we have a total of only 3, and we make sure that we have a reference, and therefore we will create non-Hispanic black, yes or no, non-Hispanic Asian, yes or no, 1 for yes and 0 for no, and then for Hispanic would be 1 for yes and 0 for no. So we have a total of 3. And now that we know that there are only 3 variables for a given study participant, we can then deduce the race and ethnicity, and we can now have a reference value. So information in our logistic regression, a brief overview, is that it uses the maximum likelihood estimation. The dependent variable is a transformation using a logit transformation, and that the betas or the coefficients, so I've introduced you to coefficient, which is the from simple regression. So right here, this is our standardized beta coefficient, so that's the most important value that we look when we are looking at SPSS. And right here now is that the coefficients of a multivariate logistic regression represent the logarithm of the adjusted ratios for each of the dependent variables. And in order to obtain the adjusted ratio and obtain the confidence interval, we actually use an exponentiated beta coefficient. So again, that is a very complex mathematical calculation, but these are all done by SPSS. And as I've mentioned, we're not going to talk about mathematics here. We're just going to talk about concepts. SPSS will do this all for us. So our hypothesis when we do logistic regression is that the null hypothesis is that attempting to lose weight in the past year will not affect the odds of going out to eat frequently, which we only have 2 binary dependent variable outcome, and that is 5 times, less, or more. And then we are looking at the adjusted beta of 0 and an adjusted odds ratio that is equals to 1. And our alternative hypothesis is that attempting to lose weight in the past year will affect the odds of going out to eat frequently, adjusting for gender. So right here, that's the difference between your null and your alternative hypothesis in logistic regression. And then we set our statistical significance at 0.05. And the model significance is the most important thing that we need to look when we interpret SPSS output is the -2 of the log likelihood. So that is -2 LL. That's exactly what we're going to look at SPSS output. And this test compares the likelihood of the alternate model. You have your null and your alternative hypothesis. And the alternative model is always with all of the independent variables that you included to that of the null model. Well, there's no variables included. And right here, this is the -2 LL, or -2 of the logarithm likelihood is that. Okay, so right here, this is the output on SPSS based on the sample data, is that the null model is 516.86 based on the iteration history table. So this is what I've mentioned in my lecture on maximum likelihood, is that it will keep on, it's iterative, and that's why it says step 1, 2, 3, and 4, and it stopped at the 4th iteration, because you can see here that 516.86 is the same 516.86 that was the calculation of the model on its 4th iteration, and that there's no more, it's the estimation terminated at number 4 because the parameter estimates changed by less than 0.001. So this is how maximum likelihood is all about, is that if the change from the 1st iteration to the 2nd iteration to the 3rd iteration is less than 0.01, it will stop there, because that's what the algorithm of maximum likelihood estimation is all about. And then it compared to the null model that is 491.34. So right here, the model summary is, it shows you that 491.36 is the value for the -2 log likelihood, so logarithm. And then the Cox and Snail R-squared and the Nagle-Kirk R-squared is between 0.051 to 0.07.8. What that tells you, always remember that the R-squared is the shared variance of the independent and dependent variables. So this is roughly 5.1% to 7.8% is, this model accounts for about roughly 5.1 to 7.8% of the shared variance of the independent and the dependent variable. And so this is another important output of SPSS when we do logistic regression, is the omnibus test of model coefficient. It uses the chi-square statistics, and so we need to review again what is chi-square statistics. Well, the chi-square statistics is a model that that demonstrate the difference between the expected and the observed frequencies of all the observations. So when we look at it uses chi-square statistics, and then it gives you the difference between the negative log likelihood of the null model and the final model. So when we look at the SPSS output, our null model was 491.34, and then we have 516.86. You subtract that because it uses the chi-square model, which is your expected versus the observed frequencies of the values. And so we have a 25.53, and that's why you will have there are 3 chi-squares that will be printed out by SPSS. 1 for step, 1 for block, and 1 for the model. And the variables were entered together, so the values for the 3 are the same. So right here, you can see that this is the omnibus test for model coefficient. For step is 25.52, for block is 25.52, and for the model, it's also 25.52. So these are all SPSS output, and all the significance are all 0.00. The next output that you will see in SPSS is the fit of data to the model. And this is the Hosmer-Limshow goodness of fit statistics. And this statistic compares the observed probabilities to those predicted by the model, and it also examines the residuals. And non-significant results indicate that the model fits. So right here, this is non-significant because it's less than 0.05. And we have a degree of freedom of 2 because we have our number of our variables is 3. So 3 minus 1 is the degree of freedom is 2. And the chi-square value for that step 1 statistics is 0.358. And so in this data set, it shows that there is goodness of fit of the data. So the adjusted odds ratio from what we can get from this is the exponentiated beta coefficient for losing weight will be 0.896. For the gender, which is the male or female gender, and this one is trying to lose weight, it's not statistically significant for trying to lose weight, but it is statistically significant for the gender. It's 0.000. And so this is now the SPSS output for the beta coefficient, which is the most important one because regression is always about beta coefficient. And then here is our constant. So this is constant again is weird why SPSS uses constant, but it means the intercept. And then that's the value of the beta coefficient of the intercept is 0.644. And then it tells you here that the gender is statistically significant. Here is the most important value when we look at SPSS in logistic regression is the statistical significance, and then this is our independent variable is with those who try to lose weight and what is the gender, and then our dependent variable is binary, which is eating 5 times or eating 5 times, more than 5 times, and then the other the opposite of that is eating less than 5 times. And so in this study, what we can then, in our conclusion then, is that trying to lose weight does not significantly affect the odds of frequently going out to eat when controlling for gender. However, we know that the value for men and women, we assign 1 for women, 0 for men. Women are significantly less likely to go out frequently with an odds ratio of 0.32 than are men. And in summary, logistic regression can be used when the outcome of interest is dichotomous. And then the independent variable can be on any scale. It could be polytomous, but we need to create a dummy variable so that we have a reference. And that the most useful result of logistic regression is the adjusted odds ratio. And the regression output give us information about the regression diagnostic, about the overall significance and goodness of fit, and that is through your this is by Hosmer, Limshow, goodness of fit statistics that should not be statistically significant. So I have 10 more minutes. Again, this is the beauty of logistic regression, is for us to use categorical variable, binary dependent variable, and then our independent variable is, we like it to be dichotomous. However, if it's polytomous, we need to create a dummy variable. It's quite complex, but it's doable. But this is the reason why logistic regression is very appealing to epidemiologists, because in epidemiology, we try to just simply expose, not expose as our independent variable, and then disease or no disease as our dependent variable. So logistic regression is very appealing to epidemiologists when you're trying to look at the relationships and the predictive power, the predictive modeling of the relationship between your independent and your dependent variable. So think of logistic regression all the time as something that you can use if you have a binary dichotomous dependent variable. And so before this video will end, I have added in the overview of statistics, I have added, so this is our collection now of the overview of statistics. I've added another table that these are the examples of generalized linear model as function of independent variable and dependent variable. And so if you have binary categorical independent variable, and then you have a binary dependent variable, the best statistics to use will be your binary logistic regression. So right here. So you have either mixed or polytomous categorical independent variable, but you need to create a dummy variable. Now, if this is really, if you have binary dependent variable and you also have binary independent variable, you can also use the log linear regression. This is a transformation. So you transform your data into by using the logit function. So these are some of the guides that I'd like you to always remember in using, in choosing your statistics. So why do we need to know this? Because when you try to defend your thesis, and I'm not trying to explain the mathematics from the very beginning, but I'd really just like us to understand the fundamental concepts of the statistics, the fundamental rules, the fundamental assumption that must be met, and then we should be able to defend our PhD dissertation with confidence because we understand the basics. All we want is that we understand the basics of statistics and that we apply it to our research question and that we understand the different types of data that we're gathering. What is it? Is it ordinal data? Is it interval data? Is it a ratio type of data? And so those rules need to be applied, and then we choose the specific statistics. And so that's it for this week. We covered, last week we covered ordinary least square, we covered maximum likelihood estimation, and then I showed you the SPSS output of simple linear regression and how it relates to simple correlations and how it relates to ANOVA, or analysis of variance. And now I'm slowly moving towards the logistic regression. And so hopefully next week, we're going to cover multiple regressions. And then I'm not going to cover Poisson. Poisson regression is for if you want to know a model, like what is the risk of someone to have a bike accident if you use path A versus path B, and then it's called count dependent variables. So if you want to know what would be your chance that you will have an accident if you are a biker, for example, in a certain path, that's what you call Poisson regression. These are count dependent variable, and we're not going to cover that. I think that's way beyond our nursing interests. But log linear model, I'll try to cover that, and also multinomial logistic regressions. Hopefully I can cover that as well. So we are done with those, and you will have your first online quiz for the different concepts. Just 20 questions, and then you will be asked to do a group test. I'll do a simple linear regression, perhaps, so that it's not too complicated. And we'll slowly increase the complexity of this course. I mean, this is what this is all about. We all struggle with this. I struggled with it when I was way back in 2006. I have a lot of study groups in the library, and because it really requires a lot of mathematical algebra, algorithm, and then it requires understanding linear equations, which is basically your y-axis and your x-axis, and the different relationships of x and y. And so for those who are very good in math, where you can plug in the values of the x and the y in a mathematical questions, I think it's a lot easier to understand linear regression. But it does take a while, and you really have to go back to the basics of mathematics and linear equation. And so I don't want you to be scared. What I want is just basic understanding. All right? Okay, and we will apply this, and we will make sure that it's more of a practical application. So we will practice. All right, so we'll do assignments, simple linear regressions, and we'll do some quizzes on what's OLS and what's maximum likelihood estimations. And it's not going to be so difficult, so not to worry so much. But this is definitely a little bit higher than what you learned from your statistics one. Okay. All right. Good. Any questions?
None.
None? Oh, sige, magbasa ha lang, review ha lang jud kay it really takes time. Okay? All right.
Okay.
Take care, everyone.
Yeah, happy weekend.
Happy weekend.
Thank you, Doc.
Okay. Bye-bye.
Bye.